These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So here's something that we learned how to calculate early in the course. Early in the course, we learned how to calculate this. What's the graphical interpretation of this?
F prime 1. Okay, so as x increases by 1 unit, function f also increases by 1 unit.
Okay, I think you got a little confused in that answer there. Well,
yeah.
So you can't say how much it increases because I didn't tell you how much the derivative was.
Okay.
So, for example, if this was 8, then this would mean that as x increases by 1 unit, the function increases by approximately 8. Since I didn't give you that number, you can't finish that. But what I was going for is, what's the graphical interpretation? What's the graphical interpretation of this concept?
The slope.
Let's be more specific.
F prime is the slope of the tangent line to the function f.
Here, this slope?
Yeah.
Or here, this slope? Or here, this slope?
Okay.
The slope where?
At 1.
Yeah, okay. So it's the slope of
The tangent
tangent line at x equals 1. Okay. Now, it's also called the derivative, of course. Now, there's a problem. How can you figure, what's the definition of a tangent line? It's really hard to define what a tangent line is. It's hard to define what a tangent line is or what the slope is here. So do you remember, how did we solve this problem? How did we define the slope of a tangent line? Well, what we did was we said, draw a line between x equals 1 and another point on the graph. Say, this point here. So this would be 1 plus h. So then this would be f of 1. And this would be f of 1 plus h. Now, how would you find the slope of this line? This line's called the secant line. How would you find the slope of that secant line? Well, remember, the slope is the rise over the run. So the rise this would be the rise, the difference between this coordinate and this coordinate. And the run, you see the run would just be h.
Right.
If you go from 1 to 1 plus h, the run is just h. That would be the slope of that secant line. That would be the slope of that secant line. But wait, there's a problem. We didn't want the slope of the secant line. We wanted the slope of the tangent line. What good does it do us to know the slope of the secant when we want the slope of the tangent? Well, the mathematicians use a clever trick here. They say, well, gee, if these 2 points are close enough, the slope of the secant is close to the slope of the tangent. So they said we could use this to approximate the slope of the tangent, because you can see this slope is not that far from this one. Well, that still doesn't seem very satisfactory. Who cares about close? We want exact answers. Well, then the mathematicians had another good idea. What about if we take the limit as they get even closer to each other? As they get even closer to each other, these secant lines are going to get closer and closer to the tangent. So the limit as h approaches 0 is going to be the tangent line. The limit as h approaches 0 is going to be the tangent line. That's going to be f prime of 1. So this is just a review of some of the stuff from earlier in the course. That was the definition of the slope of the tangent line. you can define the slope of the tangent line by taking this limit. You can approximate the tangent line with a secant, and then take the limit as the approximations get better and better and better. The limit as the approximation as h approaches 0 would be the exact slope of the tangent line. Do you remember this was the first way? Do you remember this is the first way we learned to find derivatives, right? Mm-hmm. So notice that we started with how to find derivatives. We started with the long way. This was the long way to find derivatives. It wasn't much fun. It was a pain to work it out. But then in the next chapter, we turned around and we came up with a short way. And the short way, if you remember, was just to say, if f of x is x squared, we can just memorize the power rule from the textbook and say f prime of x is 2x, right? And then what's f prime of 1?
Sure.
Well, that's a lot better, isn't it, than using the limits. So the way we studied derivatives at the beginning is first we learned a long, tedious, unpleasant way involving limits. And then we turned around and learned a short way, a shortcut. And ever since then, we've never used the long way, right? We've never used that long way for a long time. We always use the short way. So why did we even bother torturing ourselves with the long way? Well, I don't know. Maybe we shouldn't have. But the reason why the textbook does that is because you can't even define what the slope of the tangent line means unless you use this limit. This limit is the definition of the slope of the tangent line. And you can't prove that the short way works without using the long way. So all the proofs in the textbook have to use this long way to prove that the short way works. It's not really clear to me that it's all that useful for a student to learn it anyway, though, because you're not really going over the proofs. But anyway, that's the reason why the textbook teaches you the long way and the short way. All right, now the reason I'm mentioning that is now we're going to do the same exact thing for definite integrals. Now we're talking about how to find definite integrals. And we could talk about the same function as before. We could talk about the same function, x squared. Oops. But now we could try to find, say, the integral of f of x between 0 and 4. What's the graphical interpretation of this?
It's the area between the x-axis and the curve between 0 and 4.
That's right. So it would be this area here. Okay, good. Well, the point is there's also a long and a short way to find those definite integrals. Just like with derivatives, there's a long and a short way. However, there's a big difference, which is that when we did derivatives, we studied the long way first, and then we learned the short way. But remember, your instructor decided to do the sections out of order, right? Your instructor jumped ahead to the short way. Your instructor jumped ahead to sections 5.3 and 5.4, which was the short way. And now we're going to go backwards and fill in the long way. It's going to, in a way, it seems kind of pointless. Now that we've learned the short way, why should we torture ourselves with the long way? Well, because you need it for the test, basically. All right, so now we've learned the short way. Now we're going to have to go back and do it the long way. So we'll end up with a similar pattern that we did with derivatives. So just to remind ourselves, what is the short way? So remember in this case, for example, here was the definite integral we were talking about. Remember, what's the graphical interpretation of this? Well, what's the graphical interpretation of this?
It's the area under the curve between 0 and 4.
Yeah, under what curve? The x squared curve. Good.
Right.
Well, what is the short way? How would you work this out?
You find the antiderivative of x squared, and that's 1/3 x cubed, and then we take the we plug in 4 into x, and then we subtract. Yep, just like that.
All right, so we may as well get an answer.
21.333 repeating.
Good. So I guess your instructor wants those exact answers. So you can change that into a fraction.
Okay. 64 thirds.
Right. Or I don't know if you recognize it from it, it just looks like 21 and a third, right? So you could write it as 21 and a third or 64 thirds. Okay, so here's our short way. Now remember, this is really amazing that this trick works. It turns out that the way to find areas is by using antiderivatives. That was the fundamental theorem of calculus part 2. The amazing fundamental theorem of calculus part 2 is that for some mysterious reason you can figure out areas by using antiderivatives. That's a wonderful trick here. Okay, now what we have to do is learn the long way. Even though we know the short way, we're going to learn the long way. Well, again, why are we even bothering with the long way? Well, there's two reasons. One reason is you can't even define what the word area means without using the long way. So we need the long way to define what area even means, and you need the long way to prove that the short way works. In order to prove the fundamental theorem of calculus, you need to understand the long way. Now, again, that doesn't seem too practical from the point of view of a student like you because you're not trying to learn how to do proofs anyway. But anyway, that's what the class wants you to learn, that long way, and I guess that's their reasoning. All right, so we'll have to go ahead and do that. So I guess we'll go over to this picture here. So what are we trying to do? We're trying to find the area underneath this curve. Well, let me give you a simpler case. What's this? This is supposed to be a horizontal line. So what would this be?
Oh. 3 times 6, so 18.
You didn't need any antiderivatives for that, did you?
Nope.
Because it's the area under the curve. Well, this has a why did I do 1 to 4? Why make my life difficult? Let's do this. All right, what's this?
24.
Yeah, it's a base of 4, height of 6, so it's just 4 times 6. So everyone knows what area means when you have a rectangle. When you have a rectangle, area is base times the height. But how the heck are you going to even define what the area means here? You know, obviously you could say the area is a measure of how much space is here, but how could you even define how to measure that space? The more you think about it, the more confusing it is. Well, the mathematicians have come up with a trick. You've probably already seen this trick in class. The trick is approximate the area. The trick is we're going to approximate the area using rectangles. So we're going to split up this series from 0 to 4. We're going to split it up into 4 segments. 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And on each of those segments, we're going to draw a rectangle at the right endpoint. So here at the right endpoint, the rectangle is this high. And here at this right endpoint, the rectangle is this high. Notice the rectangle only lasts for 1 segment. I'm not pulling it all the way over to here. It's just over this 1 segment. And over here, the rectangle is like this. And then over here, the rectangle is like this. And we're going to use those rectangles to approximate the area. We're going to use those rectangles. So can you see if you added up the area of all those rectangles, it would be somewhere in the vicinity of the true area. It wouldn't actually be that close, but it wouldn't be twice as big or half as big. It would be somewhere in the vicinity. And if we made the intervals smaller, then the rectangles would be even a better approximation. So we're going to use these rectangles to approximate the area, kind of like we used this secant line to approximate the tangent line. Here we're going to use these rectangles to approximate the area. Does it make any sense so far?
Yep.
All right, well, how can I figure out how high this rectangle is? What's this point here? How can I calculate this point? Remember, this is the function.
That point is 1, so we can plug it in the function, and our height is 1.
And how can I figure out what this point is?
Same method, plug 2 into the function, and we get 4.
Let's try this point.
The height was 9. The height is 9.
And let's try this point.
The height is 16.
Okay, good. Excellent. So what you did here is you took f of 1, f of 2, f of 3, and f of 4. So what's the area of this rectangle?
1.
Yeah, how would you, what's the area of this rectangle?
9.
How did you calculate that?
1 times 9.
Right. So let's actually write that out. And how do you calculate this area?
1 times 16.
And this one?
1 times 4.
And this one?
1 times 1.
Okay. So what's the total area of all the rectangles together? You can use your calculator if you want.
1 plus 4 is 5, plus 9 is 14, plus 16 is 25. 25.
Check that on your calculator. Okay, so there must have been an arithmetic mistake there. It's always easy to make arithmetic mistakes, so it's good to practice the arithmetic without the calculator, but then we always need the calculator as a double check. Okay, does that mean that the area under the curve is 30? Well, no, but it's approximately 30. It's probably not that close to 30. Is this probably bigger or smaller than the real area?
Bigger.
Yeah, bigger. It's not that much bigger. You can be pretty sure the real area isn't something like 2 or 3, right? So,
yeah.
or 0.5. So this isn't the best approximation, but at least we're in the ballpark. Okay, so this is a way to approximate the area, just like we could use the secant line to approximate the tangent line. Now, of course, this wasn't a great approximation, but that's because I only split this up into 4 segments. If I had split this up into 1,000 segments with 1,000 tiny little rectangles, then it would be an outstanding approximation. So this is just to give us the basic idea. Maybe I'll draw that out so we can see what that means. All right, well, I'm tired of writing it out. But can you see that if we made the rectangles really small, the approximation would be very good?
Mm-hmm.
Okay, so that's my point. The only reason why this approximation was not very good is because we only used 4 rectangles. If we used lots and lots and lots of rectangles, the total area of the rectangles really would be almost exactly the same as the area under the curve. Okay. So if we took the limit as the number of rectangles went to infinity, that limit should actually exactly equal the area under the curve. Okay, so this is one way to figure out this area. This is the area that we worked out using, so let's see here. So how many subintervals did we use here?
Let's see, 1, 2, 3, 4.
Good. And these points that we used here are called sample points. These were the sample points. So what sample points did we use here? We used what are called right endpoints. Because from each interval, we based the height of the rectangle on the right endpoint. Okay, so now let's try this again, but now let's try using left endpoints.
Okay.
Maybe you can try this on your screen. So let's do the same problem with 4 subintervals, but let's try using left endpoints to approximate the area. Great.
So with the left endpoints, since the function starts here, you just would go over. So you would really have a dotted line like right here, right?
That's true.
Okay.
So what's the height of the first rectangle?
0.
So what's the area of the first rectangle?
0.
Now, should that amaze you? Is there really a lot of area in that first segment?
No.
It's really only a sliver of area, right? So 0 is actually not a very bad approximation. Of course, it's more than 0, but 0 is not a very bad approximation. There really isn't that much area in that first sliver.
Okay, so this function was, well, okay, so this area is 1. So
Okay. So shade the rectangle. Shade the fourth rectangle. Good. What's its height and what's its height?
16.
All right, so did you write that correctly down below? Yeah, 16. Good.
Yep.
Now shade the third rectangle. What's its height?
4.
Did you write that correctly?
Mm-hmm.
Shade the second rectangle.
I didn't write that one right. So this one was this one. That was that. I guess I was, I don't know.
Now here's kind of a weird question. Shade the first rectangle. There is no rectangle, basically.
Right.
So what's its height?
0.
And what's its width?
1.
So let's write that down. 0 times 1. So that's what messed you up. You got weirded out by the invisible rectangle. You couldn't believe that the rectangle really wasn't there. So you kind of shifted over. You kind of wrote, you wanted to write something down that wasn't just a 0 there. That's what was messing you up there. All right, so one thing we've seen here, so you're going to see a problem like this on the test, almost certainly. The instructor wants you to actually show the rectangles. One thing we saw is things are much clearer if you shade the rectangles. Things will be much clearer if you shade the rectangles. Otherwise, it's easy to get confused about what you're looking at. Okay, so let's continue.
Okay, so now we add 0 plus 1 plus 4 plus 16. That equals 21.
Okay, good. By the way, do you remember what the answer was when we used the left endpoint approach?
30, I believe.
Can you see why this answer, so is this answer bigger or smaller than the true area?
Smaller than the true area.
How can you see that?
Because the shaded area does not take up the entire space. Yeah.
But can you see that if we used, say, 16 rectangles, we would get closer to the truth?
Mm-hmm.
Yeah, okay. So fortunately, your instructor will have mercy on you, and he's not going to actually ask you to draw 16 rectangles. He's only asking you to draw a few rectangles just to get the basic idea. But if you really wanted a good approximation, you'd want to use a large number of rectangles. So there's like a conflict. To get a good approximation, you need a large number of rectangles, but that would take too long to do during the test. So just to give you the basic idea, he's asking you just to draw 3 or 4 rectangles, just to get the basic idea, even though that doesn't give you that great of an approximation. All right, remember that sometimes people can get weirded out when one of the rectangles has 0 height, so you have to be a little bit careful about that. Okay, very good. So how would we describe what we just did here? How many subintervals were there?
4.
Right. And how did we choose the sample points? In this case, the sample points were where? The left endpoints, yes. So we went over what to do with when the sample point is the left endpoint, and we've gone over what to do when the sample point is the right endpoint. Your instructor also covers using midpoints from each interval. So let's go scroll down and try this problem again for the same function. Same function, okay. Same subintervals, but now let's try to approximate the area using the midpoints from each interval. I haven't exactly explained what that means, but let's see if we can figure out what it would mean to use the midpoint from each interval. This will be a little bit trickier, but it shouldn't be super tricky.
If you average the left endpoint and the right endpoint, would you get the definite interval or like the true area?
You would get probably closer, but no, there's no particular reason to think it would be exactly right.
Okay.
There is only one way to get the true area. The only way to get the true area is, as I was mentioning, take the limit. Increase the number of rectangles to 100, to 1,000, to 1,000,000, and then take the limit as the number of rectangles goes to infinity. The only way to get the exact area is to take the limit as the number of rectangles goes to infinity. There's other things you could do to get better approximations, but they're just approximations. Excellent. Try drawing the rectangles then, based on those. Now that first thing you drew was, remember the rectangle has to extend over the entire subinterval. So the first subinterval is from where to where?
From 0 to 1.
That's right. So the rectangle has to go from 0 to 1. But you started right. First, how high is the rectangle? Show how high it is. Yeah.
There.
And now you need to draw the entire top of the rectangle. That's right. So it's a little bit trickier than before, but it shouldn't be super tricky. That's the process for getting that rectangle.
Okay. He said if we don't draw our rectangles perfectly, we might get points taken off.
Okay, well, just be perfect. Just be perfect.
Okay, so... I'll bring a ruler.
Okay. Where are you getting those numbers that you're putting on the y-axis from?
Yeah, those aren't right. I was taking it from here. It's not even anywhere near correct.
So first of all, what you have to do is label your midpoints. So for example, point to the first midpoint. Yeah. What number does that represent?
0.5.
And then the next one? Right. So the numbers you were writing down were good numbers, but you were putting them in the wrong place. Yeah.
Okay, now
what number did you write down for the third endpoint? The third midpoint?
2.5.
Okay, I just had trouble reading your writing. Okay, good. Now we have to figure out some way to figure out the heights of these rectangles. Is there any way now to figure out the heights of the rectangles so we can label those on the y-axis?
We can plug these midpoints into our function.
Okay, good. Just do the same exact thing we were doing before. Good. Okay, good. So that's a good instinct for when to use the solid and when to use the dashed lines. We want to use solid line for the actual rectangles and dashed lines for everything else. So the reader knows we're not getting confused about that.
Okay, so now I can say area equals, well, 1 times 0.25 plus 1 times 0.25 plus 1 times 6.25 plus 1 times 12.25. We get 12.25 plus 6.25 plus 2.25 plus 0.25.
Okay.
I guess it just happens to come out the same.
Oh, that surprises me. How could that happen?
Weird.
1 second. Okay, fair enough. They happen to come out the same. I was about to try to tell you that the midpoint approach gave us the best approximation, but in this case, it was just about the same as the left endpoint. What's happening here is this curve is rising pretty steeply. Because the curve is rising pretty steeply, it's going to end up that the midpoint approach is still going to underestimate the truth pretty severely here, I guess. But 1 second. Let me make sure I'm getting this right.
Okay.
Okay, that didn't make any sense. Let's go back to the previous case. Point to the fourth rectangle in the left endpoint approach. Point to the fourth.
Right
yeah.
here?
What's its height?
Its height is 16.
Tell me how you calculated that.
Let's see. We plugged in 4. We got 16. Oh, but it's left endpoint approach, so we should have put in 3. Okay. Oops.
Let's fix your picture too. Why did you write a 16 there? Well, it might possibly because you remembered having used a 16 in the right endpoint approach. But notice we never got to the 16 in the left endpoint approach. So we have to be careful. We can't just assume that all the numbers from the previous approach are going to still be relevant for the new approximation. Okay, well now this makes much more sense because obviously the left endpoint approach going to be over or underestimation of the area?
Under.
Right. And I think you can obviously see from the picture that the midpoint approach should be more accurate than the other two approaches. So that it didn't really make sense. It was giving us the same answer. That was a very strong clue we'd made a mistake somewhere. Yeah. So it looks like now we got it right. What was the answer from the right endpoint approach?
30.
And from the left endpoint approach?
14.
Notice how the midpoint approach now is nicely in between the two of those. That's usually going to happen on the problems you're doing, I think. So that now made more sense. Okay, very good. All right, so that's how we find these areas. So now this is the way that we could approximate a definite integral. We could approximate the definite integral by splitting it up into these intervals. And of course now if we took the limit as the number of rectangles went to infinity, that limit would be the exact definite integral. That's the long way to find definite integrals. That's the long way to find definite integrals. What was the width of each of the rectangles?
1.
But how do you know? How do you know the width was 1? Well, it was just kind of obvious in this case, but how would you formally, mathematically figure it out? Well, the definite integral was going from where to where? What were the limits of integration?
0 to 4.
So what's the total distance between 0 and 4?
4.
How would you figure that out mathematically? Mathematically, that would be 4 minus 0. Good. Now, careful, let's just write 4 minus 0. And then how many subintervals are we splitting that up into?
4 subintervals.
So let's write 4 minus 0 divided by divided by 4. Good. You'll have to put the 4 minus 0 in parentheses if you write it that way. And what does that come out to be?
1.
Which is the width. All right, now in this case, it was obvious you could just eyeball the width to see what it is. But as we go forward, we're going to have a mechanical procedure to figure out the width of the subintervals. That width is called delta x. Do you see why it's called delta x? Do you know what delta means?
Change.
Yeah, well, so that's the change in x along each of those subintervals. So that would be the technical, formal way of figuring out the subintervals. We'll need that as we go along.